Hello, Chem12. So what I'd like to do today is I'll go over a specific question the student asked, and then we'll look at going over the notes on the indicators, which I kind of had you look ahead on, and then we'll look at titrations a bit further. So a student asked about question number 113. There are two color changes. So each time you have a color change, what happens is you reach an endpoint. And the fact that there are two color changes within the same titration means you hit two endpoints. And what that indicates is that each endpoint you neutralize one of the hydrogens. So because there's two, that indicates there's two hydrogens or two protons. Remember, a proton is H+. So if there's two hydrogens, then this has to be a diprotic acid. And I'll kind of expand on that with what we look at today with the titrations. Another question the student asked had to do with the what does the pH equal pKa mean? So I'll get to that as well. Okay, so that's in the notes I'll be covering here. So first off, what's an indicator? So an indicator is a very complicated molecule, and so and there's many different types of indicators. So the generic term for an indicator is using HIN and IN minus. Okay, so there's no actual compound HIN. And so this pair, it's a conjugate pair, and it's unique in that each of the conjugates has a separate color. So for example, you could have a conjugate pair where the HIN is yellow or the IN minus is red. Okay, and there's lots of different colors. So similar kind of acid reaction here, right? Mixing with water, producing H3O+. So what happens is the color that's going to form, like in Science 10, you probably did that acid-base indicator lab where you had that spot plate and you added different indicators and different chemicals and you could see different colors, right? So it works off of this principle, and basically what's happening in terms of which color you get, it has to do with which side is being favored as a result of Le Chatelier's principle, right? So the same principle we looked at a few units ago. Now, when you have yellow and red, just recognize there is an intermediate color, which in this case would be orange. And orange would be where you've reached the end point, the neutralization point when we talk about titration. So let's say you're in an acidic environment. So the acid is basically going to funnel in and increase H3O+, which causes the stress of too much of that. And so according to Le Chatelier, to relieve that stress, you're going to shift left. And so you shift left, and then whatever color HIN is, that's the color that you're going to see. In this case here, because you're shifting left, and the other thing about the conjugate acid pair here, the HIN and IN minus, you start with equal amounts, so it's kind of like a balance. And so when you put it in a specific type of environment, then you basically change that balance. So in this case, HIN would be greater than IN minus, okay, because you're in an acidic environment. The opposite is true if you're in a basic environment. What's going to happen here is the OH minus is going to react with the H3O+. So it's going to consume some of the H3O+, so the H3O+ drops. And so to lift it back up, you're going to shift right. And so the IN minus is going to be favored versus the HIN in this case. And you'll get whatever color the IN minus is. So when you do, in fact, hit the endpoint, your HIN and the IN minus are going to be equal. And so this is the question a student had brought about, what does Ka equal to pKa mean? So if HIN is equal to IN minus, so this is the Ka of the indicator. If those two are equal, then this is just like a math question where these two basically cancel each other out. And so now you're just left with Ka equals H3O+. And so if you take the log of both of these, then you're going to get pKa equal to pH. Okay, so I think there was some confusion when you saw this statement in the textbook. This is not implying that this is always the case. This is only the case at the endpoint. Okay, so at the endpoint, this is what the what occurs. Okay. So let's look at a question here where it says you've got pH range of 8.2 to 10.6. Okay, so that's where the color change is occurring. And so if we wanted to find the Ka of this indicator, well, this is sort of an approximation. We'll use the middle point between 8.2 and 10.6. So we add the two up, divide by 2, so 9.4 is the middle point. And so what we'll say is the pH here, 9.4, according to this here, is equal to the pKa. And then in order to find the Ka, what we'll do is we'll take the anti-log of negative 9.4, and that gives you the value 3.98 times 10 to the minus 10. Okay, so that would be the Ka. So like I said, I'll get to different types of titration in just a moment here. When you're doing a titration, you need to select an appropriate indicator. And this is kind of how you go about deciding which indicator to use, because remember, you don't know the concentration of the of one of either the acid or the base, and then the counterpart, you know the concentration of the standard, but because you know what you're titrating, you have a rough idea where the pH endpoint should be, and so knowing that, then you select the appropriate pKa, which gives you the Ka. So this is basically how you find the indicator that you want to go with. A universal indicator is one where there's going to be several different color changes occurring over a range of pH values. You have the indicator chart on page 335 that gives you this information. So here's a question. You are looking at some unknown, and you want to basically narrow down the pH. And so what you would do is just add that unknown to different indicators and see what color results. So when you add methyl red, you notice it's a yellow color. So if you look at your chart, that means you have to be 6 or greater. If you add phenol red, you get red, which means you have to be 8 or greater. And then if you add phenolphthalein, you get the colorless color. So this means that you have to be less than 8.2. So then now, just by adding a bunch of indicators, you can narrow down the pH range. And so this is the way you can figure out what the pH of an unknown solution is. Okay, so we're going to look at titration. So remember, a titration is where you have the burette, where you have the Erlenmeyer flask, where you have what we call the analyte that's in the flask. So that's a solution of unknown concentration. And then your titrant is the standard, right? What's in the burette. And that's what you're going to put in. And then you also have indicator in the flask. And so at some point, which we call the equivalence point or the end point, you're going to have moles of acid equal to moles of base, and you're going to get a permanent color change. Now, if we were to look at the titration as it's occurring and basically monitor the pH, we'll get a pH curve. Okay, and you can do that in a titration if you put a probe in the flask, which will give you a readout of the pH as you're doing the titration. And so these are some common shapes here. So let me go through this. So this kind of refers back to that question that I began the class with, a diprotic acid. So first off, from looking at this, what I want you to be able to recognize is the pH is increasing as you're adding more volume of titrant, okay, your standard. So if the pH is increasing, what that tells you is you're adding base, right? Because remember, pH as pH gets higher, you get more basic. So you're adding base. And so what you look for are these vertical stretches, and that's common in all these titration curves. The vertical stretch is where the endpoint occurs, and you can kind of estimate midway as being the precise pH at the endpoint. And this is why it's such a very precise method, because if you let's look at this one, you know, here's right before the endpoint, here's right after the endpoint, and it's very narrow. right? So it's like we talked about, within a half drop, you're getting a permanent color change. And so the fact that there's those two of these vertical stretches here indicates that there's two endpoints, which means it has to be a diprotic acid. Here, this is a weak acid because we know we're starting at a higher pH. Okay, so remember, 7 is neutral, so it's below 7, but it's not way down here. That would be a strong acid. And then you're adding strong base. Here, you've got a weak base, and we're adding strong acid. Okay, and so the pH is dropping. And then here we've got a strong acid, strong base titration. You're adding strong base because the pH is going up. And because this is a total neutralization, your pH at the end point is going to be 7. The other thing you can look at in terms of the differences between these curves is when you have something weak, you get more. You don't get a more of a flat part of the curve. Like here, you get kind of an area like this. It's not flat. Like this one is, right? See how this one's more flat, and so that's an indication that it's weak. Same here with the weak base part. You get an area that's kind of more curvy, as opposed to something like this with the strong base. Okay, so strong acid, strong base gives you more of a rigid kind of shape, whereas weak gives you a little more of a curve. And again, the vertical stretch is where the end point is occurring, and the midpoint of that vertical stretch is the exact location of the end point. Okay, so you see that for each of these ones. So you should be able to look at a curve, and just from the picture, whether it's going up or down, you should, and the sort of the shape and where you begin or where you end, you should be able to figure out what is being titrated. Strong acid, strong base; weak acid, weak base. Right? Which two of those four are involved? Okay, so let's go through these more. Through calculations now. Okay, so weak acid, strong base titration. Equivalence points can be greater than 7, right? So remember, 7 is neutral. So weak acid, strong base, a strong base dictates, right? And so that's why you have a pH greater than 7 at the end point. Now, the textbook shows you how to derive this. If you take the Ka and write out the expression, it works out to Ka equal to H3O plus 1/2. So what the 1/2 means is this is the halfway point on the graph in terms of the volume that you're adding. I'll show you what I mean by that with an example. And then another calculation here is Ha, which represents weak, just generically represents weak acid. The weak acid concentration can be found from this, and that's just derived from the ICE table. Okay, and then the counter to that is the weak base strong acid titration. So here the strong acid is going to dictate. So your pH at the equivalence points can be below 7. So again, go back to the previous page and look at the pictures, and you'll see that that's verified. And then here, because we're working with a weak base, we're going to look at Kb. And so this is a similar type equation to that one up here. And then here's your weak base concentration. Okay, so again, selection of indicators based on what type of titration it is. This gives you a kind of a ballpark estimate of what indicator you should be using, the appropriate indicator. Okay, so let's get into an example here. So here you've got some weak base, and it's got this pH, and then you have 25 mils of that base, so in a flask. So that's the analyte, and then you're going to add HCl, which would be the standard, so you know the concentration of that. And here's the pH of the mixture at 18.4 mils, and a total of 36.8 is required to reach the endpoint. Okay, so the halfway point then would be at 18.4, because 18.4 is half of 36.8. So the Kb, so using the above equation, the Kb is equal to the concentration of OH minus at the halfway volume point, so the 18.4 mils. So we've got the pH, so let's find the pOH at the halfway point. So we go 14 minus 7.047, that gives us 6.953. Take the negative anti-log of that, and that gives you 1.1 to the negative 7 molar for OH minus, and then we can just call this 1.1 to the negative 7 for the KB. Okay, so remember this is no units for KB, right? Just like KQ. What's the concentration of the base? So now we have the KB. Okay, so what we need is the OH minus, and so the initial POH was 10.104. So subtract that from the initial pH was 10.104. Subtract that from 14 to get the POH, and then use the negative antilog of that, and there's your hydroxide concentration, 1.27 to the negative 4, and then put that into the above expression. And that gives you 1.27 to the negative 4 squared divided by 1.1 to the negative 7. So that gives you 0.15 molar for the weak base concentration. Okay. So I'll get you to do these questions here on page 176, okay, 125 to 129. So you can have that done for Friday. And then I'll give you some more topics on Friday. So in terms of where we are, we're kind of getting near the end of the acid-base unit. We're on a good pace in terms of like finishing the course. Right now, we would have roughly about 5.5, 6 weeks left in regular class time, right? So basically, like I said, we're near the end of the acid-base unit. Then we have the electrochemistry unit, and then I'll give you a bit of a review. Then I'll give you a final exam. Okay, so we're on pace where we'll be able to finish the course. Again, for those of you who are going to be taking first year chem at either college or university, they are going to be covering many of these topics in more detail there. So the better you are familiar with these, what we're going through, the better, easier that'll make that first year for you. So again, make sure you're doing the questions, and then just ask if you look in the back of the book, it doesn't really make any sense, and you need some explanation on that. Just make sure you ask me, and I can begin class by going over any questions you have. All right, so I'll stop there. Again, let's look after yourselves, be safe, and I'll talk to you again on Friday. Okay, bye for now.